Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The next speaker is Vanessa Witz from Versailles, who is going to talk about discrete log of elliptic curves on various things.
Thank you. So first of all, I would like to thank the organizers for inviting me to this really nice conference. So in this talk, I'm going to present you index calculus methods on elliptic curves over extension fields, and also a very useful algorithm which computes the four traces, which will be really efficient for our index calculus approach. So in the first part of this talk, I will give you some background on this index calculus method. So we are mainly interested in the classical elliptic curve discrete logarithm problem. So we consider an elliptic curve defined over a finite field, and we take a rational point on this elliptic curve, and usually P is as a large prime order. And we take a point Q in the subgroup generated by P. The goal is to find the X such that Q is equal to X times P. So of course, to tackle this problem, you can always use the generic algorithms such as baby step, giant step, or Pollard's law. But what is interesting with these elliptic curves is that you usually only have this generic algorithms. We have seen, however, that on the first day of this conference, that in some cases you can also try to transfer the DLP on the elliptic curve to a group where it's weaker. So this is what we do when we consider transfer methods. For example, we can try to transfer this DLP on finite fields. So using a pairing, you can transfer the DLP on the subgroup generated by P to the multiplicative group of finite field, which is FQ to the power K, where K is the embedding degree corresponding to this group generated by P. And so this famous move, Menedez-Okamoto-Thomson attack, will work only when K is relatively small, which is not usually the case for a random elliptic curve. We know that K is usually of the order of Q for a random curve. So this will work only for very specific families of curves, for example, supersingular curves. Otherwise, you can also try to lift the DLP, the elliptic curve to a characteristic zero fields, for example, the p-adic number fields. And in this case, again, the attack works for very specific families of curves only when the curve has a subgroup with a power of the characteristic base field. For example, for an anomalous curve, that is the curve which has the cardinality equals to the characteristic, you have a polynomial algorithm. So this is really efficient, but really specific. When the curve is defined over an extension of a field, you can also try to make a transfer via the descent to the Jacobian of a curve, which is defined over FQ. The problem again here is that the genius of this curve is usually exponential in n, so these kinds of attack will work again only for very specific families. So we, except from these transfer methods, we only have generic attacks, and what we like to do during this talk is to make some analogous of what we have on finite fields or hyperelliptic curves, that is, use an index calculus method. So as far as we know, we don't have any equivalent for the moment on elliptic curve defined over prime field. But the good news is that it's already feasible when the curve is defined over an extension of a finite field. And these methods are usually asymptotically better than Bayes descent or generic algorithms. So I recall here the basic outline of this index calculus method in a slightly different way than the pre-computation and descent way. So first we define a factor base which consists of some points in the curve. And then we have a stage of relation search during which we try to decompose one combination of the base point P and the target point Q into a sum of points in the factor base. And once we have collected enough independent relations, at least the cardinality of the factor base, we deduce with linear algebra techniques the DLP of the point Q in the base P. Okay, so the results that we have here come first from Gaudry and Diem. For a curve defined over fq to the power n, we have a complexity for n fixed, which is in soft 2 of q squared minus 2 over n, as q goes to the infinity. So this is better than generic methods as soon as n is greater than 3. And Klaus-Diem has also proved rigorously that this algorithm is sub-exponential as soon as n grows as fast as the square root of log q. But unfortunately, the constants that are not written here are exponential is the square of n, as n goes to the infinity. And in fact, these methods won't be applicable as soon as n is greater than 4. So that's why we have proposed with Antoine Joux a variant, which seems to be worse as q grows to the infinity, because it's in soft 2 of q squared. But in fact, it has better dependency when as in n. So we still are faster than generic methods as soon as n is greater than 5. And what is interesting here is that this method will work on base field, on a field which has an extension equal to 5, a degree of extension equal to 5. So asymptotically, we can see also that our methods is more efficient than the generic algorithm or Gaudry or Diem approach. As soon as n is between the logarithm of q and the third root of the logarithm of q, as n and q goes to the infinity. Sorry?
The previous slide had the constant omega. What was it?
Oh, I'm sorry, I didn't. Yeah, this constant omega comes from the multiplication of the matrices, so it's a constant between 2 and 3. I will go.
You need to stay under 3. You need fast multiplication.
Yeah, if you're not on the, yeah, that's a good question. If it's equal to 3, actually, you get something in n squared there. So on your on this figure, you just have the square of the logarithm of q. Yeah. So now I'll go deeper into details about these endless calculus methods. So our goal here is to collect at least the cardinality of f decomposition of random combination of the base point and the target point. So at this point, we need to define what kind of decomposition we can do on elliptic curves and what kind of factor base we should consider, because this is not really obvious. And in fact, the first question was answered by Semaev in 2004. He had this clever idea to consider a decomposition here in a fixed number of points of the factor base. By doing that, you can actually use the group law that you have on your elliptic curve to have this equivalence here. Namely, R is decomposable as a sum of n points as soon as the x coordinates of this point is a root of what we call here the m plus 1th Semaev summation polynomial. So this is interesting because we convert the decomposition search into a resolution of a polynomial. So this works on any kind of curves. You can define the curve over any kind of field. This will always work because you only use the group law. I will talk about Nagau's alternative approach later in this talk. Just to say at this point that instead of considering decomposition into a finite number of points, you can also consider the functions that are vanishing in these points. So we'll see later how it works. So at this point, Semaev didn't have the convenient factor base, and Pierre Gaudry has then proposed to consider elliptic curve defined over extension field. This is a nice idea because then it's really natural to consider for the factor base the elements that have an x coordinate lying in FQ. And so the cardinality of this factor base here is Q, so we need to collect at least Q decomposition. And to solve, to find the roots of this semi-F summation polynomial here, what we do is a sort of Bell restriction. So we see simply we see FQ to the power n as a vector space of dimension n over FQ. And we look at each coordinates of this polynomial in this vector space. So we get n equations in the variable xpi, and whose coefficients are depending only on the x coordinate of the point R and the coefficient of the curve. So each time we want to try a decomposition, we will need to solve this kind of polynomial system over FQ. We can add also some additional optimization here. We see that we have inherent symmetry in our problem. We consider decomposition into points. This is symmetric. So we can reduce the total degree of this polynomial system by exploiting these symmetries. And we can also diminish the number of elements in the factor base by considering this quotient here by the natural involution that we have on elliptic curves. By doing that, we get only Q over 2 independent relations to compute. So as we see here, the main difficulty is to solve the polynomial system to get decomposition. So we will focus here on a slightly more general problem. Namely, we will consider the computation of the variety of an ideal in dimension 0. We'll discuss this later. But you know that for the univariate case, when n is equal to 1, we have polynomial algorithms such as Gantor's and House. So the univariate case is really easy. Although but the multivariate case, it's much more complicated. And what we do in general to solve this problem is that we use elimination theory. So we try to find in the ideal a univariate polynomial. And from the solution of this univariate polynomial, we deduce the elements of the variety of I. So at this point, we can use two techniques, either a resultance or a Gromner basis. And since Gromner bases are really efficient, I will focus on this right now. The main result is we are using here is the shape lemma, which tells us that if you compute a Gromner basis for the lexicographic order, you will get a set of representatives of your ideal, which has this shape here, with a univariate polynomial in the last variable, which is of degree of the ideal. So I say this is for most zero-dimensional ideals. If you consider a general case, you can be assured that you have always such univariate polynomial in the last variables. So the idea here is really simple. Once you get the lexicographic basis, you find the solution by finding the roots of the last polynomials, and then you evaluate in the other polynomials to get a variety of I. So of course, since we know that solving multivariate polynomials is an NP-hard problem in general, computing such Gromner basis will be very difficult. The complexity of such computations is a bit difficult to estimate, but we have a worst-case upper bound. For example, in the general case, we have this result from Meyer and Meyer, who tells us that it's doubly exponential in the number of variables. And in dimension 0, you see here that if you compute the Gromner basis for the lexicographic order, you have a complexity which is in d to the power bigger of n cubed, where d is the degree of the polynomials and the number of variables. And it's d to the power of 2 on n squared for a degree graded reverse lexicographic order. So maybe you will see what's the point of this. For computing a lexicographic order basis in dimension 0, we will prefer to compute first de Grave-Lex Gromner basis, and then use a change of order algorithm to get the solutions, the lexicographic order Gromner basis. So I can give some sharper points on the complexity of these two steps. So here, for the de Grave-Lex Gromner basis computation, we consider the number of monomials that we can have in n variables up to degree d-reg. So d-reg here means the degree of regularity of the ideal. You can understand it as the larger degree reached during the computation of the Gromner basis. And there's some hypothesis. So consider this number of monomials to the power omega, where omega is the constant used in the matrix multiplication. The change of order is in the degree of the ideal to the power 3. You can use, for example, the GLM algorithm to do that in dimension 0. So now we are able to analyze the original attack of Gaudry's algorithm, of Gaudry, sorry. So the idea here is to consider decomposition into exactly n points, where n is the degree of the extension of the base field. So by doing that, we get as many equations as unknowns, and a total degree of the polynomial system, which is 2 to the power n minus 1 after symmetrization. Clausim has proved rigorously that this ideal is of dimension 0 and of total degree 2 to the power n times n minus 1, which somehow corresponds to the Bezos theorem. Okay. And the probability of getting one decomposition is then about around 1 over factorial n. So we will need to solve at least factorial n times q systems, since the factor base has a cardinality equal to q. Concerning the complexity of this attack, since the ideal has a very large degree here, 2 to the power n times n minus 1, the most difficult part comes from the FGLM algorithm. So the dominating complexity for each trial, each decomposition trial here, is in the degree of the ideal to the power 3. As we need to repeat this factorial n times q times, we will get a complexity for n fixed, which is in soft tau of q here. The linear algebra step will be in n times q square, because we are looking of a vector in the kernel of a very sparse matrix, which has only an element per rows, and which is of size q per times q. So at this point, it's quite natural to want to make a balance between the two steps, and this is what Gaudry has done. He applies a double large prime variation à l'Aterio to get a complexity which is in soft tau of q squared minus 2 over n. So we can also deduce the complexity in n, which is as this shape. And at this point, I would like to mention that this rebalance is not always necessary. If you consider fields, curve defines over fields for n equal to 4 or 5, with not too large q, just a q useful for the cryptographic applications, this rebalance won't be necessary. In fact, the first part of the algorithm will be the most costly. So it's not really interesting in the practical application. Okay. So as I've said, the degree of the ideal is really large, and this is quite a bottleneck here in this approach. We could hope to do something better by saying that most of solutions are, in fact, in the algebraic closure of FQ and not in FQ. To get only the solution in FQ, what we could do is to add in the ideal the equation for the base field. But unfortunately, this won't work because Q is too large in practice to get any benefit from this. So we're kind of stuck with this very large degree here. That's why, I have made an example, a lesson 101 example before of this Gaudry's approach, just to finish the presentation here. So we consider a curve defined over this small field here, which has a prime cardinality. We take 2 random points on this curve, so we know that they are related by some x, since the cardinality is a prime number here. And we take a random combination of these 2 points, and we consider the fourth symmetrized summation polynomial of the semma f to get the decomposition of this point R. So this polynomial has this shape. It's 4. I mean, it's here in 3 variables, if you symmetrize in the 3 first variables, up to degree 4 here, and you have exactly 35 monomials. That's all the monomials that you can construct up to this degree. So it's a very full polynomial. You do your restriction, your van restriction, you get this system here. You compute the Grobner basis of the corresponding ideal with the lexicographic order, and you get what is expected with the shape lemma. That is a univariate polynomial here, which has the degree to the power 3 times 3 minus 1, which is 64. So we consider the solutions, as I have explained. And here we get 2 solutions. So we try to see if the corresponding polynomial has some is split and has all its roots lying in the base field. If it's true, it will maybe give us a decomposition. So look at what we have here. The first roots give this polynomial, which is irreducible over the base field. So we don't get any relation from this. And the second root gives us this polynomial, which is split over the base field. So we look at the x coordinates coming from these roots, and we see if we get a point on the curve corresponding to this x coordinate. In this case, it's working. So we get this relation here. We have seen that we need to collect at least Q over 2 relations. So in this case, it's 54 relations. And after that, we can deduce with linear algebra the squared logarithm of Q in the base P. So this was a little example. And I told you that instead of considering here this semma summation polynomial, we could also try to apply the Nagau's approach. So in this case, what we do is that we consider the function that are vanishing in the point R and at most 3 other points. So this is the vector space considered in the Riemann-Roch theorem. It's of the dimension 3, so we can get a basis of this vector space, which is generated by these 3 functions here. So what we are looking for a function which is in this vector space, so which has this shape after normalization at the infinity. So it only depends on the constant lambda, on 2 constant lambda and mu here. And we are looking for the roots of this function. And we only want the roots corresponding to the 3 points in which it's vanishing. So what we do is we first get rid of the y variable, and then we divide by the monomial x minus xr to get rid of the point r. And we get this polynomial of degree 3, which has coefficients depending on the 2 constant lambda and mu. We want this polynomial to be split over f1 and n1, and to have all its roots lying in the base field. So this gives us a polynomial conditions. Namely, we want to find lambda and mu in this field, such that these coefficients are in the base field. After doing sort of L restriction, we will get 3 variables coming from each of these variables. And here we need to have at least the last two components to vanish. So this gives us a polynomial with 6 variables and 6 equations, which is quadratic in lambda and mu here. Okay? So instead of having a semi-F summation polynomial, we need to solve this polynomial system here, which is quadratic in 6 variables and 6 equations. And actually, you can show with Grobner basis computation that this is slower than the original attack on the case of elliptic curves. So this approach, in fact, won't be relevant for the elliptic case, but of course it has some practical interest. First of all, it's applicable for on hyperelliptic curves, whereas semi-F doesn't work. We don't have any equivalence of semi-F there. And also it can give us a way to compute the symmetry summation polynomial in the case of elliptic curves. What you do in this case is you identify the coefficients with the elementary symmetric polynomials. You perform an elimination of the variables lambda and mu, and then you get directly the symmetrized summation polynomial. So this is also interesting. So now, as I said, the main bottleneck from this first approach is the degree of the ideal involved for each decomposition trial. What we try to do here with Antoine Joux is to lessen this degree. So what we do is we decompose in n-1 points instead of n points. By doing that, we get an overdetermined system, which is generally of dimension of degree 0, or exceptionally 1 when there is a solution. So this is what we wanted. And the price to pay in return is that we need much more decomposition trial before getting 1. We will need actually a factorial n-1 times q trials before getting 1 relation. So in practice, this won't be a problem because we are very efficient to solve the polynomial systems involved. First, we will see that we only need a degree-of Grobner basis computation, and there won't be any need to change the order here. And secondly, we can also try we will also apply our F4 algorithm, or variant of the F4 algorithm, which take benefit of the fact that we need to solve always the same systems, the polynomial system that have exactly the same shape from one trial decomposition to another. So with these two facts, we will get good results. And to convince you that this method is quite simple and quite simpler than the first one, I will illustrate this on the same field with the same curve. So I take a new random combination of the base point P and Q. And in this case, since I want to decompose in only 2 points, I will only use the first symmetrized semi-F summation polynomial. I can write it completely here. So after that restriction, you get this ideal. And when computing the degree-of Grobner basis, you get these representatives of the ideal. And you see here that it's already solved in S1 and S2. You have mainly two cases at this point. Either you get 1 for the Grobner basis, or you get a Grobner basis which is already solved, because the degree of the ideal here is 0 or 1 exceptionally. So we consider the corresponding symmetrized polynomial. We get these two solutions here, so we are very lucky because we get a solution, a decomposition of our first point R. The remainder of the algorithm is exactly the same as the Gaudry's one. To summarize what we have seen for this index calculus method, I put all the complexity on the slides and the feature of our polynomial systems. So for Gaudry and Nagao, we see that we decompose in exactly the same number of points, and that the corresponding ideal is of the same degree. The main difference is it concerns the features of the polynomial system. Here we get a quadratic system with this number of equations and variables. Here we have only n equation and n variables of degree 2 to the power n minus 1. And this makes quite a difference with the complexity of the resolution of the polynomial system. We see here in the exponents of 2 that this gives us almost twice the exponent that we have here. So this is much slower. For our variance, we decompose in n minus 1 points, so we get a degree of the ideal which is 0 almost in all cases. We have to try much more decomposition to get Q relations, but the complexity here is quite better than the one we have here. It might be to you, appear to you that it's almost the same, but in fact, having omega against 3 and n minus 1 times n minus 2 against n times n minus 1 is quite a difference in practice. And anyway, this is just about theoretical upper bounds. We see in practice that we can do some things. So now the second part of my talk, I will mainly speak about F4 traces computation and the algorithm that we can use to speed up the computation of the Grosvenor basis. Maybe it's time to define what a Grosvenor basis is. So just to understand the algorithms, I give the definition here. So we consider an ideal a multivariate ideal. And we said that a set of representative of this ideal is a Grosvenor basis when the initial ideal of I is equal to the ideal generated by the leading monomials of these polynomials here. So this is a Grosvenor basis. And the main results for computing them comes from Bohrberger's PhD thesis. So he considers mainly two operations on the polynomials. The first one is the S polynomials. It's a combination of two polynomials such that you cancel the leading monomial. Okay? And we also have a reduction of a polynomial with respect to a list of polynomials, which is somehow the equivalent of the classical division polynomial in one variable. Okay? The main result is that this set of polynomials is a Grosvenor basis if and only if the remainder of all the pairs, the S polynomials that you can compute, is equal to 0. So having this result, it's quite easy to get an algorithm which computes the Grosvenor basis. What you do is you start from the set of representative of your ideal. You consider all the S polynomial that you can do with these polynomials. You compute the rest, the remainder, with respect to the current basis, and each time is different from 0. You put it, you add it to your base. By doing that, you increase the corresponding initial ideal. So as we are in the Noetherian ring here, at some points the algorithm will stop. And when it stops, you get your Grosvenor basis. So,
sorry, I'm just trying to trace through this. How does the S polynomial depend on the definition of the ideal? So this is supposed to be G1 up to GS is a Grosvenor basis for the ideal I. Does S depend on I?
Yeah. So this is representatives of your ideal, in fact. And this is a specific set of representatives. They all verify this condition. And if they all verify this condition, then it's a Grosvenor basis of your ideal.
Polynomial S is the same for every ideal I. It doesn't depend on I.
This definition, it depends only on the two polynomials you put here.
So how come you couldn't take a subset of G1 up to GS and then it would still satisfy these conditions, but it wouldn't be a Grosvenor basis because it's not enough for the whole ideal.
And what you do at the, sorry, the first part of the algorithm is you're starting from a set of representative of your ideal.
You have to have a complete set to start.
Yeah, you take, for example, F1, Fr, and then you compute all the S polynomials that you can do with a couple of these polynomials, and you compute the remainder. Yeah, this is an iterative algorithm. Yeah. Okay. So we have an efficient way to implement this Bourberger's algorithm, which is due to which is an algorithm due to Jean-Charles Fougère, which is called F4. And the main idea here is to use linear algebra techniques to reduce at once a large number of S polynomials. So we are not doing this one by one, but we take a number of large S polynomials to reduce them at once. So to select, you need to define a selection strategy to do that. So for example, in practice, we usually consider the S polynomial having the lowest total degree. Okay? And what you do is you construct a sort of Macaulay-style matrix. That is, you put in the matrix all the multiples that are involved here in your S polynomials. So you put in this matrix all these multiples, and you also put the polynomials that are useful for computing the remainder by the current basis, the current base. So you have this huge matrix. You perform a reduced row echelon form, and you get then the reduction of all your S polynomials with respect to your current base. So this is a very efficient algorithm, but there is still one problem with this algorithm, which is the same with the Bourberger's one. It's that most of the time you are computing reduction to zero of your S polynomials. Despite Bourberger's criteria, you will get a lot of reduction to zero. So that's why Jean-Charles Fougère has proposed in 2002, an elaborate criterion which tells us a priori to skip a given S polynomial. So we have some signature condition of this on the polynomials, and we check if the signature will verify the criterion, and if it's not, we skip the reduction. There is one drawback. One drawback for this F5 algorithm. Namely, you won't be able to compute any kind of. You won't be authorized to reduce any polynomials that you want. So during the computation, you will have some incomplete polynomial reduction, and even worse, you will have some redundant polynomials that you can get rid of. So what we would like to do here for our index calculus methods is not to take these multipurpose algorithms, but instead take advantage of the fact that we have many polynomial systems with the same shape to solve, and use this information to get rid of these S polynomials that are reducing to zero. So we would like to have a sort of F5 criteria that allows us to skip these unnecessary reductions. So here is the outline of our variant. You have two subroutines. A first routine that you run on the first system. So you consider a classical F4 algorithm. You construct during this algorithm a list of all the multiples that are involved in your computation. And each time you have a reduction to zero, you remove from that list a well-chosen multiple. Then for the subsequent system, you will use the second subroutine, the F4 remake algorithm, which uses this pre-computed list to compute the Gromner basis. So instead of having a queue of intuited S polynomials, you will pick directly from that list the relevant multiples that you need for your Gromner basis computation. So in fact, this idea is not really new. People who are working on Gromner basis over a rational field can sometimes use a reduction modulo several primes and make the computation of the Grabner basis modulo these different primes and get the original Grabner basis by using a Chinese remainder theorem. They do that because when you compute directly the Grabner basis over the rational, you get very large coefficients, and you want to avoid that. So we can do this kind of reduction here. And of course, when you do that, reduction modulo several primes p, you will have a lot of time the same computation of your Grabner basis. So that's why Traverso has proposed in 88 a precise definition of these Grabner traces for the Bobager algorithms in the case of rational numbers. But unfortunately for us, this analysis is not precise enough to give us good results in the case of in the situation that we have in index calculus methods. So what I would like to do here in this part of the talk is to give a precise analysis of the behavior of this F4 variant. So I need to introduce some terminology here. I will introduce the notion of biometric family of polynomials. So this is simply polynomials that have coefficients which are depending on some parameters. And we consider instances of this parametric family as some specialization of these parameters. And we would like to know when F4 remake will compute successfully the Grabner basis of these instances of our first parametric family. So I will define what I call generic behavior here in the following way. So I assume that I am able to compute, at least theoretically, a Grabner basis of the parametric family with the F4 algorithm, at least theoretically. And I will say that the instance behaves generically during the computation as soon as we have exactly the same number of iterations during the course of the algorithm, and that we have at each step exactly the same leading monomials and the same S polynomials. It's clear that if our instance verify this generic behavior, in this case, the F4 remake algorithm will compute successfully the Grabner basis. Okay, if we have run the first subroutine on a generic system, then for other generic system, we will get a good Grabner basis with F4 remake. Okay, so now that we have this terminology, I would like to give you an algebraic condition for this generic behavior and estimate the probability that F4 remake computes the right Grabner basis. So I will assume that until the step I-1, the instance behaves generically. And at step I focus on the two matrices constructed by F4 algorithm. So I have the matrix Mg for the parametric system and the matrix M for the instance. So if I have S leading monomials in my ideal at this step, what I do in the Magterly matrix is that up to I exchange some of the columns and some of the row to get here a triangular matrix. So we put on the first columns the columns corresponding to the leading monomials. Okay. And we put one polynomial on the first rows that are corresponding to this that have these leading monomials. So we get a matrix which has this size here, this shape here. Okay, sorry. So it's quite difficult to explain. So for the instance, we have a specialization for the parameters. But since the polynomials are already normalized at this point, we get exactly the same shape for the first part of the matrix. So if I perform a reduced relation form on the first part of the matrix, I get exactly the same shape for the parametric family and for the instance. Okay, now I would like to focus on this submatrix here, I would like to make a reduced regression form of this matrix and to see what's happening for the instance. So I select the columns corresponding to the pivots in green here. I put them on the left part of this matrix, and I perform a reduced regression form. I get this shape for the matrix here. For the instance, I don't know if after specialization I don't have any cancellation of the corresponding pivots. But if you don't have any cancellation of this coefficient, you will be certain that you will have exactly the same shape for the instance. So you will have a generic behavior for the instance in this case. So I have now my algebraic condition that the system behaves generically at step I if and only if this matrix here is of full rank. Okay, this is quite a simple idea. And to get the probability that this actually works, I will do some heuristic assumption. I will suppose that these matrices have a uniformly distributed coefficient over FQ. So at this point, I would like to remember how we have constructed our systems. We consider a random combination of two points, the base point P and the target point Q. And we suppose here that the group law is mixing up sufficiently the coordinates to have something that is really random for the x coordinate of R. Since our polynomial have coefficients only depending on this x coordinate, I will suppose that we are sufficiently close to the uniform distribution to make this heuristic assumption. So now it's really easy to estimate, or at least to give an underbound for the probability that the matrices have full rank. I can give this upper bound here, and since we have n step during the computation, I have the probability that the system behaves generically, which is greater than CQ to the power n step here. And as you see, when Q grows to the infinity, this probability is really close to 1. So when Q is large enough, we will have very good results. So here I give the experimental results of for an elliptic curve defined over an extension, a degree extension equal to 5. I suppose that I have run a pre-computation over an 8-bit field, and this computation has been done in about 9 seconds. And now I'll look at what's happening when, for example, I consider an elliptic curve defined for a P having 32 bits. The probability of failure here is very low because P is really large. It's about this. And if I look at the timings given by F4 remake in this case, we get the Grabner basis computation done in less than 8.5 seconds, which is 3 times faster than the classical F4 algorithm on the same implementation, of course. For comparison, I also give the timing from Magma, which is considered as the best implementation of this algorithm for the moment. And we see that it's much faster in this case. So it's fair here to want to compare our variant to the F5 algorithm, since both algorithms are considering no reductions to 0. And as I said at the beginning of the second part of the talk, the problem with F5 is that it's computing many redundant polynomials that we cannot avoid because of this F5 criterion. And after an implementation of this algorithm on my computer, I get about 17,000 labeled polynomials at the end of the computation of the Grabner basis, against only 2,700, about 800 with the F4 variants, or the classical F4 algorithm. So we see at this point that it's not possible that this F5 algorithm could be faster than our variant in this case. Okay. So finally, I will give you some application of all this stuff to cryptography. And we'll consider here an application to the Static Diffie-Hellman problem, which is a non-standard version of a non-standard problem of the family of Diffie-Hellman problem. So the main observation here is that once we have a way to decompose it to a factor base, it's quite immediately that we get an algorithm that is able to solve an oracle-assisted version of the Static Diffie-Hellman problem. So this has been discovered independently by Robert Ganja. So maybe I should recall you what I call an oracle-assisted Static Diffie-Hellman problem. You consider a finite group G and a secret integer D. And during a learning phase, you are allowed to ask an oracle any multiplication by D that you want for any point in the group G. And after this learning phase, you are given a previously unseen challenge X, and you are asked to compute D times X. Okay, so if you have a way to decompose into this factor base, you have a way to solve this problem. What you do is during the learning phase, you ask the oracle all the multiplication of the elements in the factor base by the secret integer D. And after this learning phase, you will decompose X in the factor base and then deduce the multiplication of X by the secret D. Of course, as we have seen, it's not clear that X is decomposable in the factor base. So what we do here is we multiply by a random integer, X, and at some point this multiple here will be decomposable in the factor base. So when you get the decomposition, what you do next is the multiplication by the inverse of R modulo the order of the group, and then you get, of course, the decomposition of your point X. So for this application here, the first remark is that we don't need any linear algebra step. We only need one decomposition. Okay, so the second part of the classical index calculation methods isn't necessary. And the other remark here is that we need, during the learning phase, to do Q/2 oracle queries, which is quite a lot. And to palliate this problem, Ganja has proposed a nice idea. What he does is a technique à la Harley to balance the two stages by reducing somehow artificially the factor base. You take some elements only of the factor base, so you decrease the probability of decomposition, but you won't have you will have less oracle queries to do. Okay. So this part is joint work with Robert Ganja and was announced on the number 3 release. So a nice application here of our algorithms is to consider this standard curve proposed in the IPsec protocol. This is the Oakley well-known group 3 curve. So this curve is defined over the finite field F2 to the power 155. This is really nice because this extension here is of the degree, can be seen as an extension of degree 5. And what we do here is, as we can decompose it into 5 points, we aren't able to compute decomposition into 5 points because the Grabner basis computation here is too hard. So what we do is our version of decomposition, we decompose in 4 points. So we get a polynomial system that has this shape. It's composed of 5 polynomials that have a total degree equal to 8 in 4 variables. And to get one relation, we will need to test about 50 billionth decomposition. So we do this with magma, for example, to see how long it takes. Its decomposition takes about 1 second with MAMA, which is not good enough for a good attack here. But with our variants and dedicated optimization, we are able to go down to about 23 milliseconds, which is good timing. If you have access to 8,000 processors, you can do the attack in less than 2 weeks. So this is somehow a feasible attack. Yeah, that will be the end of my talk. Thank you.
Thank you very much. Other questions? Yes?
Your color chart had numbers on the y-axis, but no numbers on the x-axis. Log Q, what should I think about the numbers there?
The first chart?
You had a chart in colors with...
Yeah. Going back to this. It's at the beginning. Sorry. Is that a way to go faster? Oh, yeah. Here? Yeah, because it's for very large value of Q, so it's an asymptotic. I'm looking at an asymptotic behavior here. So, is that answering your question?
Maybe you already said this, but so in practice, what values of n can you handle? You gave examples of 3 and 5. How much can you push that?
Actually, for index calculus methods, we haven't any results for attacking the DLP. We have only a practical implementation for the Oracle-assisted static Diffie-Hellman problem. So for the Oracle-assisted static Diffie-Hellman problem, the best we can do is this n equal to 5 case.
How long would it take you to compute the Oracle assistance?
That's a good question. I suppose that you have to ask something like a smart card or a chip. Or I don't really know, but it will be a very long time. It's just I feel, yeah, in some ways, you can paralyze this computation, so it will be very long. I can give you any timings, but
I did that field, so I was, and then Gaudry said I have an attack, and so far nothing is better than the square root attack. So.
Yeah, actually, yeah, you're right. We can do anything better than the square root attack, so this is always interesting. Yeah. Yeah.
Other questions? No? So let's thank all the speakers of this morning session again.